I think it's kind of fun. And this is section 7.3, sampling distributions. So to start with, we're going to have notation for populations and notations for our samples. So our population parameters are mean is mu, standard deviation sigma, size. We very rarely actually know the size of our population, okay, but if we did, we could call it capital N, and our proportion would be P. And then sample statistics are X bar, S, N, and P hat. Okay, this is something, by the time you do your homework and things, you need to know this very well, okay? Because when it comes time for the test and I use one of these symbols, you need to know if it's a parameter or a statistic. So we start with the concept that if you have any population, then there's going to be many different samples of size n that you could actually choose. Okay? So when you picture sampling 100 people on campus to find their heights, there's not just a set 100 people to choose. I could choose 100 people, and if you randomly chose 100 people, you would probably get different people. And one other person might choose 100 people, and they would get probably different people. Okay? So there's all these different samples that could be chosen. So for a very basic example, let's say that a population is just the numbers 0, 1, 2, 3, and 4. Now, normally your populations are a lot bigger, but then it would be impossible for us to list out all the combinations. Okay. So for this very basic population, let's find all the possible samples of size 2 that could be chosen without replacement, because usually if I go out to sample people, I don't want to look at the same person twice. That's not going to give me as much information as if I look at 2 people. So we want to sample without replacement, and we don't care about the order. Okay. So what are my samples? I could choose 0 and 1. I could choose 0, 2, 0, 3, 0, 4. Okay. What's my next sample that I could choose? 1, 2, 1, 3, 1, 4. Notice I don't have like a 1, 0 because we said order doesn't matter, and I don't have a 1, 1 because we're doing it without replacement. Okay. We have 2, 4. Oh, 2, 3, and then 2, 4. Not that everything has to be written in order, but I find it's a lot easier for me to not miss anything if I make sure I write them in order. And my last one is 3, 4. Did I miss anything anywhere? Can you see anything that I missed? How could we double check and make sure that we got the correct answer? Or the correct number of possible samples? Okay. Okay. We have 5. We want to choose 2. Do the combination. Gives me 10. So there should be 10 different samples. And I believe I found 10 of them. Okay, so I can double check and make sure I found them all. So think about that. For just 5 possible population values and sample sizes of 2, there were still 10 different samples I could choose. Now picture when you have millions or billions of people in a population and you want to choose a sample. How many possible samples do you think there are? Okay, there's going to be thousands, millions of samples. Now for our sampling distribution, since there are different samples that could be chosen, any sample statistics, so like your sample mean, sample median, sample mode, sample first quartile, sample maximum, any statistic that you can think of to compute is going to have its own sampling distribution, because what happens is your sample or your statistic is going to be different based on each sample. Okay, and so because it has different possible values that it could be, it's its own random variable. Okay, so each statistic is a random variable because its value changes from sample to sample. Because I don't know in advance, until I know which sample I pick, I don't actually know what value I will get for my statistic, and that's what makes it a random variable. Because it's a random variable, it can have its own distribution, which we call the sampling distribution. And then just the idea that our statistic can change from sample to sample, that's what we call sampling variability. So if you ever see that term come up again, that's what it refers to, just the fact that the statistic changes from sample to sample. As always, this is a lot easier if we try an example and see what happens. So for example 2, let's calculate the sample mean of each of the samples from our last example, and we'll also calculate the range and maximum value for each sample. And then for the standard deviation, because that takes a really long time to actually calculate, I just gave you all the sample standard deviations. So for the mean, if my numbers are 0 and 1, how can you find the mean of those two numbers? The mean is add them up and divide by 2. So my mean for this one is going to be 0.5. The mean for my next sample is 1. Then 1.5, 2, 1.5, 2, 2.5. Okay, and again, as I'm, no, that's not 2.5, is it? Oh, no, it is 2.5. Okay, again, as I'm going through and looking at these problems, I'm just adding the two numbers and dividing by 2. So 2 plus 3 is 5. Again, divided by 2 is 2.5. That's a 3 and 3.5. Okay. Notice, again, for each one of those 10 samples, I get different sample means. Okay. So can you see how your estimate of your population mean is going to depend a lot on which sample you chose? Now I go on to the sample range. Remember, range is just maximum number minus the minimum number. So 1 minus 0 is 1. 2 minus 0 is 2. 3 minus 0, 3. 4 minus 0, 4. 1, 2, 3, 1, 2, 1. And correct me if you see any arithmetic that I do wrong. And finally, sample maximum. Maximum is just the biggest number in the data set. So biggest numbers are 1, 2, 3, 4, 2, 3, 4, 3, 4, 4. Okay. And again, finally, this sample standard deviation, which I already calculated for you. Again, notice as you look at these that based on which sample I get very different sample statistics. And the fact that the sample mean has 10 different possible values, okay, means that it has its own distribution. Some of the values are repeated more than once, but each sample has its own sample mean. Okay. And the range, maximum, and standard deviation all have their own sampling distributions as well. So what we're going to do with this is we're going to draw a histogram or probability distribution function or a graph for each distribution. Okay. So for our sample mean, how many times did we get 0.5? So look up at there, how many times did we get 0.5?
1.
1. So for my 0.5, I'm going to go up to 1. So I'm just counting how many times I got each mean. How many times did I get the 1? You guys have to count for me since I can't see them all. How many?
1.
4?
Oh, the mean.
Yeah, how many times did I get 1 for the mean? 1. Okay. 1.5?
2.
2. 2? How many times did I get a 2?
2.
How many times did I get a 2.5?
2.
No, is it only 2? Thought it was a little bit more. Okay, 3?
1.
3.5.
1.
4?
0.
0, didn't get anything. Okay, so that's what my sample mean looks like, the probability distribution function. Okay, and so I look at it and I say, okay, well, what are the most likely values I could get for my mean? Most likely values would be 1.5, 2, and 2.5. What is the shape of this distribution? Okay, it looks fairly symmetric, right? Okay. Let's try the range and see what kind of distribution the range looks like. So how many times did I get a 1 for my range? 4? Okay, a 2?
3.
3?
2.
And 4.
1.
And that was it, right? Okay, how would you describe the shape of this distribution? Okay. It looks to me like it is a right skew. It would have the long right tail. My most likely value is 1, then 2, then 3, then 4. Okay. And sampling distribution of the sample maximum. So how many times did I get a 1?
1,
A 2?
3.
Is 3, 3, and 4, 4? And this would be a nice left skew distribution with my long left tail. The most likely maximum is a 4, which makes sense. Okay. And the sampling distribution for my sample standard deviation, notice again, is a nice right skew one. Okay. Notice I did this in megastat, which is why these are percents instead of counts. So notice we had 4 different statistics, and we found the distributions for each. Notice they all look like different distributions. Okay? So each different statistic could have its own sampling distribution. The sampling distribution that we're going to care about the most is the sampling distribution for a sample mean. Okay? So let's say an automaker designed a new mid-size model for sale to the public. Last year, the automaker made 6 pre-production cars of the new model. So at this moment, our population is only 6 cars because only 6 cars actually exist. So we start with a really small population. 2 of the 6 cars were randomly selected for testing, and the other 4 were sent to auto shows at which the new model was introduced. Now, they didn't want to test all of their 6 pre-production cars because then, before the auto shows, because then they have like higher mileage and the value is lower. So they only wanted to test 2 of them, so our sample is 2. So they needed a preliminary estimate of their gas mileages to report the car show. So they tested 2 cars, found mileages of 30 and 32. So the sample mean for that sample is 31. So that's what they reported at the car shows, is that their estimate for the mileage is 31. And they were using that sample mean as an estimate of the population mean, mu. Now, just a sample of 2 cars wasn't very reliable, so after the car show, they tested all 6 models, and the results of the gas mileages are the 29, 30, 31, 32, 33, and 34. Probably some nice made-up numbers. So let's find the probability distribution and the histogram describing the population of the 6 individual car mileages. Okay. So if you had 6 cars, what is the probability of drawing out that one car that had a mileage of 29? It's going to be 1/6. And in fact, each of these probabilities is going to be 1/6, correct? Okay, so if I'm just pulling out one car at a time, the probability for each individual car is 1/6. So my probability histogram looks like this. Okay. Again, that is for my individual mileage. Now, one thing I could calculate is, because I actually know the entire population, I could go through and I could calculate my population mean mu. And to find the population mean, I add up all the values in the population and divide by 6, since there are 6 of them. And I get 31.5. So my population mean is 31.5. How does it compare to the sample mean we found above of 31? Fairly close. Fairly close. A small bias. Okay. Well, technically, it was off by a little bit, but the expected value of my sample mean would be equal to my population mean. So it's not technically biased, but it was off a little bit. So now let's go through and let's find all of our possible samples of size 2 that could have been chosen and their means. And then we'll find the probability distribution and draw the histogram. Okay. So I've already done some of the work for you. So for all the samples, so I could have picked the 29 and 30, 29, 31, etc. And here are all of the sample means. So all we need to do, okay, is find the frequency for each one and the probability and then graph it. Okay, so let's go through. You guys can help me count. How many times do you see a 29.5? It looks like 1. And how many samples were there? 2, 3, 4, 5, 6, 7, 8, 9, 10. 15 samples, so the probability of getting the 29.5 is 1 out of 15. Okay, let's see, what about the 30? I see I only see 130. So its probability is again 1 out of 15. 30.5, 1, 2, I see 2 of them. 31, 1, 2, 2 of them again. 31.5 is 1, 2, 3. 32, 2 of them. 32.5 is 2 of them. 33 is 1 and 1. So for the probability for each of these sample means, it would be 2 out of 15, 2 out of 15, 3 out of 15, 2, 1 out of 15, and 1 out of 15. So let's graph the probability distribution function here. So for my 29.5, so let's do 1 out of 15, 2 out of 15, and 3 out of 15. Okay. So the 29.5 gets to go up to the 1, 30 goes to 1, 30.5 goes to 2, 2, and then we get a 3, 2, 2, 1, and 1. Okay. How would you describe the shape of that distribution? Symmetric, skewed, unimodal, bimodal? Okay, symmetric, okay, probably unimodal, because it has my really one big peak. Notice something here, okay? So we started off, our original population looked like a kind of a uniform distribution, where it's kind of rectangular. And then when I found my sample means, even though I only had a sample of size 2, now it's starting to look a little more like what? A little more like the normal distribution. Okay, and that was only with a sample of size 2. Okay. So notice though that as we went through, so we found all of the possible sample means. And because I found all of the possible sample means, it's actually a population now of sample means. So my actual population of my sample means is the 29.5, 30, 30.5, 31. Okay, so that's actually a population now of sample means. Not my population, my original individual values, but a new population of possible sample means. And it's all the possible sample means I could get, and it changes based on which sample I choose. Okay. And we found the probability distribution function for the population for all of those possible sample means, and we call it the sampling distribution of my sample mean. Questions to here? Now, so far, we've only dealt with populations of like 4 or 6 values, and so it was actually possible to know all the values of the population and to find all the possible samples. But in practice, we don't know all the values in the population. If we did, we wouldn't need to actually try and estimate anything. Okay? And our list of all of our possible samples would be too big to find and work with. Okay? But there are some theoretical properties of the sampling distribution of the sample mean that we know, and then we can figure out. Okay, so for instance, just really quick, as we come back and look at this one, okay, we knew that as we found our sample, it looked more like the normal distribution. Also, as we went through, a lot of our samples didn't give us the exact population mean. So like a sample mean of 33.5, that's not equal to my population mean of 31.5. But notice what is the most likely value for my sample mean. It is 31.5, which is actually equal to my population mean. And the most likely values are clustered around the actual population mean of 31.5. So our sample mean is still a good estimate of our population mean. So we're going to look at a few applets to try and discover some of these properties. And think of the following questions as we explore the applets. So like, what does the sampling distribution of the sample mean look like? Does it matter what the original population looks like? Okay, what happens to the sampling distribution of the sample mean if we have a really weird shaped original population? How does the standard deviation of the population of all the possible sample means compare to, okay, so notice the symbols here. So mean, mu x bar, that's the mean for the population of all the possible sample means, versus mu is just the mean of the original population. And the standard deviation of x bar versus the original standard deviation of the individual values. Okay, and how does the standard deviation of our sample means change based on our sample size? So think about all of those things as we try and do this applet. So to familiarize you with this applet, okay, you have your parent population. This is the original values, okay, individual values. Notice that the default is starting us with a nice normal distribution. For my original distribution, I have a mean of 16. Also, the median is 16 because it is symmetric. And my standard deviation is 5. So that is my original parent population. Let's say I want to look at the sample mean for a sample size of 2. Okay. What I can do is I can pull out one sample. So notice it picks 2 individual values from my original population, and here is my sample mean. I can pick another sample. Notice 2 different values gives me a different sample mean. Another 2 different values gives me another sample mean. Okay, another 2 values gives me another sample mean. So let's find 10,000 samples. Okay, so by the time I found 10,000 samples, what does my sampling distribution and my sample mean look like? It's normal. Okay, even though I only have a sample size 2, my sampling distribution, my means is 2. Okay, how about the standard deviation? Or let's look at the mean first. So my mean of my parent population was 16. The mean of my sampling distribution for my sample mean is, I went from 16 to 16.02. Okay. Now the reason it's not exactly the same is because I only found 10,000 samples, and there's probably like 10 million possible samples that I could have chosen. But if I had all of the possible samples in the world, this 16 would be 16, and this would be 16 as well. Okay, what do you think happens if I try and find a mean for a sample size of 5? So I'll do 1 for 2 and 1 for 5. If we do 10,000 values, notice here's my sampling distribution for n equals 2. Here's my sampling distribution for n equals 5. Okay. Notice which one has a bigger standard deviation. So bigger standard deviation is for size of 2. Whereas when I made my sample size bigger, my standard deviation got smaller. What happened to the mean? So my mean 16.07, mean 16.01. Okay, so both of them have means that are very close to my original population of individual values, but the standard deviation, well, let's just look. So my parent population standard deviation of 5. When I go to sample size 2, my standard deviation drops to 3.5. When I go to a sample size of 5, my standard deviation drops to 2.22. And so as my sample size increases, my standard deviation gets smaller and smaller. Why would we care about that? Okay, well, if you look at these things, let's change this one to make it even more dramatic. Let's go to a sample size of 25. Okay. So which one of these two distributions do you think is going to be more likely to give you a good estimate? Okay. Or to rephrase that, let's see. If I was to take a sample size 2, it seems like it'd be pretty likely for me to get a value up here. Correct? Or not pretty likely, but I could still get a value up here. What's the probability of getting a value that far away from the true mean on this distribution? It's going to be approximately 0. Okay, notice how for a sample size of 2, my values are still kind of close to my population mean, closer than the original individual values. But when I go to sample size of 25, now all of my sample means are even closer to the original population mean. So it has that smaller variance. So that was starting with an original normal distribution. Let's say I want to start with a uniform distribution, or fairly uniform. I didn't draw that very straight, but kind of uniform. So let's see what happens to my sizes of 2 and 5. Okay, Okay, so even though I started with a rectangular distribution, notice for my sample size of 2, it still looks more like a normal distribution. It's not quite normal because it doesn't have the whole bell shape. It's more of just a lump. Okay, but it does look more normal than the original population. Okay, what about the mean? So the mean for the top one is 16.19, 16.23, 16.14. So it looks like the means are all still fairly close. Standard deviations, 9, 6, and 4. Okay, so my standard deviations still get smaller. Let's try an even bigger sample size. Okay, so at 5, I'm looking pretty normal. At 25, I will be even more normal, although it is slightly hard to see on here because their pixels are too big. What if I pick something that looks definitely not normal? Like that. Definitely not normal, right? Okay. Let's start with a sample size of 2. Notice at a sample size of 2, it still looks kind of interesting, right? It still has lots of modes, and that's because my original population had lots of modes. Okay, but it is trying to look a little more normal. By the time I get to 5, it looks pretty normal. By the time I get to, like, say, 16, it looks even more normal. Okay, and again, I have, for my means, 15, 15, 15. My standard deviations, though, go from 10 to 4.5 to 2.5. So we're going to go through some of the results we found. So like the standard deviation, sigma of Xbar, for the population of all of our possible sample means is less than sigma, which was the standard deviation for our original population. What this tells us is that sample means are less variable than our individual observations. And the reason why is that your sample mean averages out your high and low sample measurements. Okay. So for instance, I thought of this explanation last semester. Let's say I have a population like this. So this is my population of individual values. Okay, and then I want to find the sample means. Okay, so let's say I'm just picking 2 values. Okay, if I pick 2 values from here, okay, then my sample mean will be that value. If I pick 2 from here, my sample mean will be this value. Okay, but what happens if I get 1 from here and 1 from here? It'd be in the middle, okay? And I'd probably then get another one from here and another one from here, and I'd get one in the middle, and probably another one in the middle, another one in the middle, and so I'll probably end up with some kind of distribution that looks like this. And notice this distribution already has a smaller standard deviation than the original population because a lot of my values are going to be close to the original mean. So you average out your high and low values. And because your sample means tend to be closer to your population mean, then it's going to be a better estimate than your original individual values. So it's a better estimate of your population mean. And the bigger your sample size, the better estimate your sample mean will be. Okay. Now let's go back to the apple and look at, do the sampling distributions of statistics other than the mean, so i.e. like the median, the range, the standard deviation, etc., do they still look normally distributed? What do you think? Do you think they will or not? Any guesses? Okay. Well, let's start with the normal distribution. Okay. Let's try and find, let's look at, like, say, the median, and then let's find, like, the standard deviation. And let's even put our sample sizes all the way up to 25. Okay. And take 10,000 samples. Okay. So it looks like my standard, or my median, because my original population was a normal distribution, it still looks fairly normal. Okay, my standard deviations you can't really tell on here. I made it too small, but it's actually a skewed distribution. I thought I changed it. Okay, notice it's not super skewed, but it is kind of skewed. Let's find something that's more obvious. Okay. Notice when I started with this weird parent population, okay, that my medians are not normally distributed. I have this left skewed clump right here, and then I also, if you can see it, have another clump down here. Okay? And again, my standard deviations are kind of skewed as well. Or let's say I wanted to find like the range and the variance. Okay. Notice that my variance seems really weird. I have one really tall bar and just a few bars, and my range as well, just a lot of values right here, a few values and a few values. Okay. So even though the sample mean is going to have a normal sampling distribution, the other values are not necessarily normal. And then just so you have it when you're studying, I took lots of images, lots of snapshots, okay? And so we have our original population and then different sample sizes. Okay? So like for population 1, notice I started off with a normal population, so sample size of 2 still looks normal, 5 normal, 10, 30, 100, they're all normal, but the standard deviation gets smaller and smaller. Okay, if I start with a really right-skewed population, then notice at a sample size of 2, it's still right-skewed, but it's trying to look more normal. Even at 5, it's still a little right-skewed, but trying to look normal. At 10, I'm looking pretty normal, normal, normal. Okay, with this multimodal population, so at 2, it's still multimodal, still kind of multimodal, and here at 10, again, I'm looking pretty good. At 30, I'm looking really good. And then just a few facts for us. So the mean of all of your possible sample means is the same as the mean of your original population. Okay. This tells us that means mu of X bar equals mu. So the mean of all of my possible sample means is equal to my population mean. The standard deviation of all my possible sample means gets smaller and smaller as the sample size increases. And the way that we find this arithmetically is it turns out that it is the standard deviation of the original population divided by the square root of n. Does that look familiar? We've gone over this result at least twice before, except we've usually done the variance as sigma squared over n. And what is the shape of the sampling distribution of the sample means if we start with the normal distribution? Okay, so if we start with the normal distribution, then the shape for our means is going to be normal for any sample size. Okay. Now, if I start with a non-normal population, then what will be the shape of my sample means? Okay. So let's come back up and look at the second two populations, or well, I guess second and third populations. What is the shape of the sample means? How would you describe those?
They become normal as the sample size.
Okay. They become normal as the sample size increases. Okay. Now, how big your sample size needs to be before it looks normal depends on how non-normal your original population was to start with. If it looks fairly normal to start with, it's not going to take too big of a sample size. If it's really weird, it's going to take a bigger sample size. Now, we're just going to restate this a couple times, just in different ways, mostly because it's very essential, probably one of the most essential things we cover in this class, and so we want to make sure that you got it. So the sampling distribution of X bar. So assume our original population has mean mu and standard deviation sigma, and we randomly select a sample of size n. You do need to have it be a random sample so that all of these observations are independent from each other. Then our population for all the possible sample means has a normal distribution. Now it's exactly normal if the original population was normally distributed. And that will hold for any size of sample. But it's going to be approximately normally distributed for any original population if the sample size is large enough. Now, our rule of thumb for that is if n is at least 30. And that's actually a pretty conservative rule of thumb. The mean is mu of x bar equals mu. Standard deviation, sigma x bar, is sigma over the square root of n. Again, we've proved these two formulas several times in this class. Okay, the next thing is the central limit theorem. Again, we've already gone over it in this class, but in a slightly different context. So now we say if the sample size n is large enough, then the population of all your possible sample means is approximately normally distributed for any original population. Okay? And as your sample size increases, then your normal curve becomes a better and better approximation for your sampling distribution of x bar. And again, our rule of thumb is if our sample size is at least 30, we can assume that it's going to be normally distributed. So with that in mind, then we can use the normal distribution to find probabilities about our sample means. So for example, if we want to use the normal distribution to find probabilities for the sample mean, we are now going to use a new standardization formula. Okay? Because we know to standardize is our random variable minus the mean of the random variable divided by the standard deviation of the random variable. But now our random variables are x bars. So you need to minus the mean of x bar and the standard deviation of x bar, which ends up being the formula x bar minus mu over sigma over the square root of n. So this is our new formula. Make sure when you find any probabilities with the normal distribution that you use the correct formula based on what you're working with. Okay. Now, we can only use this formula if the original population is normally distributed or my sample size is at least 30. So let's try it. The number of gypsy moths caught in a trap is discrete and very skewed. Okay, so my original population is definitely not normal. The population mean number of moths caught is 0.5, so mu equals 0.5, and the standard deviation is 0.7. Okay. Now this would be for all the possible traps. Okay. Now Paul only checks 60 traps. What is the probability that the mean number of moths is greater than 0.68? So we want to find a probability associated with sample mean. Now technically you guys have already done problems like this, correct? When we did section 5.2, our combinations of normal random variables. And so to do this, I'm going to standardize. I'm going to do x bar minus the mean of x bar over the standard deviation of x bar. Okay, so it's greater than 0.68 minus what is the mean for x bar? So we know that if my population mean is 0.5, then my mean for x bar is going to be 0.5, and my standard deviation is 0.7, but I have to divide by the square root of my sample size. So this will be the probability that z is greater than 1.99. So if I go to my standard normal table, so I'm looking for a z value of 1.9, and then 9 would be the last column. So it looks like that probability is 0.9767. But where does that 0.9767 go? To the left? So if I need to do 1 minus that to get my correct probability. So the probability that he gets a sample mean number of moths greater than 0.68 is only 0.0233. So questions on this problem where we actually work something out. The next problem, example 6. The scores of all the high school students in the nation on the ACT exam were roughly normally distributed with a mean of mu equals 19.2 and a standard deviation of sigma equals 5.1. And I forgot to tell you how big my sample size is. So we have a sample of 25 students. Let's say that it is a random sample of 25 students. So what would be your standard deviation of Xbar? And how did you find that?
I took the given standard deviation, 5.1, divided by the square root of 45.
Which gave me?
1.02.
1.02. Okay? So that's the standard deviation of Xbar. So I could ask you things like that. Or I could tell you, what's the probability, okay, that just one randomly chosen student scores at least 21 on the exam? Okay. So this is asking, what's the probability that one randomly chosen student scores at least the 21? Okay. Is this asking you for a probability associated with a sample mean? Okay, no. This is just the probability that z is, not z, it's still an x. X is greater than or equal to 21. Okay. It's just one individual. So when I try and standardize this, it's still just going to be x minus the mean over the standard deviation. Okay. Greater than or equal to, so 21 minus my mean of 19.2 over standard deviation of 5.1. So it's the probability that z is greater than or equal to 0.35. Again, I'm going to have to use the complement rule, so 1 minus, and I go to my z table to find my 0.35. So 0.35 puts me at 0.6368. So 0.3632. So there's about a 36% chance that just one student is going to score at least a 21. Whereas number 3 says, what is the probability that a sample of 25 randomly chosen students has a sample mean of at least 21 on the exam? Okay, now I'm actually looking for the sample mean, so I'm looking for the probability that X bar is greater than or equal to 21. And when I want to standardize that, I have to use a different standardization formula. So it's going to be x minus the mean over sigma over the square root of n. So 21 minus my 19.2 over 5.1 over the square root of 25. $1.76. Anyone else? Now again, when I look at this, I'm going to need to use the complement rule. So this equals 1 minus, so I'm looking for a z of 1.76 now. So So I need to go down to 1.7. Let's see, 0, 1, 2, 3, 4, 5, 6. So it looks like it's 0.9608. But again, that's the area to the left. I wanted the area to the right. So 1 minus, I forgot what it was, 0.9608. Which is 0.0392. So the probability of just one student getting at least a 21 is 36%. The probability of the sample mean being at least 21 is only 3%. And that's because, remember again, our sample means are going to be closer to original population mean, so they're tightened in, and so the probability of getting in your tails or extreme values is going to be smaller and smaller. Okay. Now notice my sample size was only 25. Why was I able to use the normal distribution? Because it's pretty close to 30, so you'd probably be okay either way. But it told me that my original population was normal to start with, so it really didn't matter what sample size I had. Okay. The next thing I might ask you is, like, how big of a sample would you need if you want to ensure that the standard deviation of Xbar is less than 2? Okay. Well, we know that our standard deviation of Xbar is defined as sigma over the square root of n. And right now we know our population standard deviation is 5.1 over the square root of n. So what do you need to do to find a sample size that gives you the standard deviation of Xbar is less than 2?
You just have to solve for it.
Just solve for n. So 5.1 over the square root of n is less than 0.2. Solve for n. So 5.1 is less than 0.2 times the square root of n. And so square root of n is greater than 5.1 over 0.2. Wait, not 0.2, just 2, huh? And so then n is greater than 5.1 over 2 squared. So it looks like we only need a sample size of 6.5 or bigger. Now you can't sample 6 people, so let's go with at least 7. Except I keep thinking no. Okay, so I need at least 7 if I want my population, or my sample, the population mean my sampling distribution to be less than 2.
We always